Hello, everyone. This is the fifth lecture from Managerial Microeconomics. That's 6701. Uh, I am going to be talking through the PowerPoint presentation. If at any time you fall behind or you want to read or I go too fast, you can go ahead and hit pause in the video. Uh, a lot of times the sound quality on this video isn't very good, so you may need to turn up the volume all the way or find yourself a pair of speakers so you can hear what I'm saying. Sometimes some noise canceling headsets might work too. Uh, Here we go. Let's begin. I'm going to talk about elasticity. As you can see, the definition of elasticity is the percentage change in a dependent variable resulting from a 1% change in another variable. We have seen how the demand for the ith good depends on the price of all the goods and income. Since there are too many variables, right? In this case, we have n prices and income. Uh, I'm going to assume that except for the price of the ith goods, all prices and income are kept constant. Now I can draw our familiar demand curve. You're going to see the figure in the next slide. To find the market demand curve, I add up horizontally all the market demand curves of different people, and I'm going to get, like I said, the market demand curve. Here's the next slide that I told you about. We can think of these first two downward sloping demand curves as the demand curves of individual consumers. If I add up the horizontal distance between the first demand curve and between the second demand curve, right, I take that horizontal distance, I'll come up to this point right here on the third demand curve. Now we can think of this summation of these horizontal distances of two demand curves as the market demand curve. One of the interesting things about demand curves is if I have a market demand curve, let's call it xi, that depends on the ith price, the price of all of the goods in the market, and on the whole distribution of income. Now if I change the distribution of income, even if I keep total income constant, all the prices constant, demand's still going to change. And the reason for that is because people have different demands, and if you give some people more money, they'll buy more of some goods and not the other. Therefore, the aggregate demand depends not only on total income, but also on who has it. So I can think of our demand for good X, right, as a function of the price of that good, the price of all other goods, and the distribution of income of everybody in the market. Now let's talk about the slope of the demand curve. The slope is very important in calculating elasticity, as we'll see later. The slope, right, to characterize a demand curve, we're going to look at the slope. The slope tells us how sensitive the quantity demanded is to changes in price. The slope tells me what the change in demand with respect to a change in price will be. In this case, it's the partial of xi with respect to its own price. For example, if a demand curve is very flat, a small change in price is going to result in a big change in demand, and vice versa. If it's very steep, then a large change in price will only result in a small change in demand. The problem with the slope is that it's not unit dependent, and therefore it can cause us problems if we try to compare two different commodities that are measured in different units. For example, we obtain a different number if we measure in pounds per dollar than if we measure in grams per yen. So if we want to get a measure of sensitivity with respect to price, that is a unit-free measure of sensitivity, we need to look at percentages. So instead of looking at the change in xi with respect to a change in price, what we're going to look at is the percentage change in xi relative to the percentage change in the price, in this case pi. So we can write these percentage changes as the following. We can write it as the change in xi over xi, which gives us a percentage, and the change in PI over PI. Uh, Now these measures are going to be unit free. It'll say something like a 1% change in price will result in a 3% change in demand. Since we expect demand curves to be downward sloping, the elasticity measures for demand are always going to be negative. The elasticity is the absolute value of the previous expression. As we said before, we can write the elasticity of demand as a percentage change in the quantity demanded of xi over the percentage change in price. Here we write that expression a little differently. I'm going to replace the deltas that I had before that gave us a big unit change with the partial deltas. And if you look at the expression in the previous slide, right, which was delta x over x or delta p over p, we can rewrite that expression as follows. That's pi over xi multiplied by the partial of xi with respect to pi, or the change in xi when pi changes. Now when I take the absolute value of this, I get the elasticity of demand. Suppose we have a demand curve that's a straight line, just like the figure below. The elasticity at every point in the demand curve is going to be different. Up high, right, it's going to be very elastic, and down below it's going to be very inelastic. Let's look at point A. The elasticity of demand at point A is very high because a small percentage change in price is going to lead to an infinite percentage change in demand. We say that's elastic. If we go down below and look at point B, the elasticity there is inelastic. In this case, it's going to be 0 because a big percentage change in price is going to result in a small percentage change in demand. In fact, it's going to be 0 percentage change in demand. In between, we have point C, and I'm going to assume that at point C it's unitary elastic. That means elasticity is going to be equal to 1 in absolute terms, and therefore a 10% change in price is going to equal a 10% change in the quantity demanded. In general, as we said at the beginning of the lecture, I can measure elasticity as a percentage change in one variable divided by the percentage change in another variable. In this case, x and y. I can rewrite that as the change in y over the change in x multiplied by the quantity of x divided by the quantity of y. Now this applies to demand as well as supply, and it'll apply to any dependent variable that is affected by an independent variable, as per the definition at the beginning of the lecture. The type of elasticity that we're going to work with the most in this class is called point elasticity. And point elasticity is simply the elasticity at a given point on a function. So this type of elasticity is simply what we've been working with. The percentage change in y with the percentage change in x, which I can rewrite as we see there. And then finally, I can take those big deltas, those big changes, and make them minuscule, holding everything else constant. Or in other words, I can write them as partial derivatives, right? So the partial of y over the partial of x multiplied by the quantity of x divided by the quantity of y. Another type of elasticity is known as arc elasticity. An arc elasticity is simply elasticity over a given range of a function or line. So the difference here is that we're using a range on the y and x axis, and instead of using a point or a quantity of x and y, we're going to use an average over that range. So arc elasticity is going to be the change in y divided by average y over that range, the whole thing divided by the change in x divided by the average x over that range. So I can think of it picking 2 points, y2 and y1 on the y-axis and x2 and x1 on the y-axis. I can write the arc elasticity as y2 minus y1 divided by y2 plus y1 divided by 2. Now that's simply the average of the range, y1 and y2. I take that whole and I divide it by x2 minus x1 and I divide that by the average x, which is x2 plus x1 divided by 2. So rewriting that, I can write y2 minus y1 as a change in y, and x2 minus x1 is a change in x. I rewrite that just like I did before. I have the change in y over the change in x multiplied by x1 plus x2, the range of x, divided by y2 plus y1, the range of y. That's arc elasticity. For the rest of this course, in general, we're going to concentrate on point elasticity, but it's good to know that there are other measures of elasticity that are just as valid. Price elasticity of demand is defined as the responsiveness of the quantity demanded to changes in the price of the product, holding constant the value of all other variables in the demand function. Remember, demand curves are downward sloping the vast majority of the time, therefore, our measurement of elasticity is usually going to be negative. We measure elasticity with the Greek variable epsilon, and the price elasticity of demand we're going to measure with epsilon p. Therefore, we're going to use the absolute value of epsilon p to measure price elasticity. If the absolute value of epsilon p is greater than 1, we say demand is elastic. If it's equal to 1, we say it's unitary elastic. And finally, if epsilon p is negative, we say demand is inelastic. With elastic demand, the change in price changes the quantity demanded by a larger percentage than the change in price. This means that for every 1% increase in price, quantity will decrease by more than 1%. Therefore, revenue, which is defined as price times quantity, will decrease since your increase in price is less than your decrease in the quantity demanded. The opposite happens with inelastic demand. Revenue actually increases. And finally, with unitary elastic demand, revenue remains unchanged. We have seen that there's different ways to measure price elasticity of demand, for instance, point price elasticity and arc elasticity, but there are also different types of elasticities of demand, and elasticity of supply for that matter. Right now we're going to talk about different types of elasticities of demand. We've already talked about price elasticity, which is simply the percentage change in the quantity demanded divided by the percentage change in price. The other two types of elasticity we're going to talk about is cross price elasticity, which is the percentage change in the quantity demanded of a given good I, we'll call it, divided by the percentage change in the price of another good, J. The next type of elasticity we're going to talk about is income elasticity, and that's simply the percentage change in the quantity demanded of a certain good divided by the percentage change of income of the consumer. Let's talk about cross-price elasticity of demand. As we said earlier, it was simply the percentage change in the quantity demanded of one good divided by the percentage change in the price of another good, or as the definition reads, the responsiveness of demand of one product when the price of another product changes. When we're talking about the other product, we can put this in two categories. The first one will be substitutes. In other words, these are goods which we substitute away from the good that we wanted to buy before. In other words, the price increases and we substitute into another good. The other type, or the other category, are complements. Complements are simply those that go, for instance, peanut butter and jelly. If the demand for peanut butter increases, there's a good possibility that the demand for jelly will also increase. For a substitute are related products for which a price increase for one leads to an increase in demand for the other. The definition for complements are similar. Related products for which a price increase for one leads to a reduction in the demand for the other. Now, when we talk about the cross-price elasticity of demand, the measurements are going to have different signs depending on whether the products are complements or substitutes. If two goods are substitutes, then the cross-price elasticity of demand will be positive. If they're complements, they'll be negative. Now, if the two goods are independent, neither substitutes nor complements, then of course the cross-price elasticity of demand will be zero. Now, let's talk about income elasticity. The definition for income elasticity is simply the responsiveness of demand to changes in income, holding all other variables constant. As with other measures of elasticity, we can write income elasticity in different ways. Here we settle on writing it as the partial derivative of demand with respect to income multiplied by income divided by demand. We can break goods into three different categories using income elasticity: non-cyclical, countercyclical, and pro-cyclical. Let's start with countercyclical. Inferior goods are goods for which consumer demand declines as income rises. Now, these inferior goods tend to be countercyclical because as GDP increases and we become richer as a nation, we demand less of these goods. Now, for these inferior or countercyclical goods, income elasticity of demand is negative. The next type of good we want to talk about are non-cyclical goods. These are also known as normal goods. When income rises, we buy more of these goods, but the percentage change in the quantity demanded for these goods usually is less than the percentage change in our income. The next type of goods, which are pro-cyclical, also known as superior luxury goods. These goods increase with income, but the percentage change in the quantity demanded for these goods is actually larger than a percentage change in income. So these are goods that we buy more of when our income rises, but we buy a lot more of. So this is basically the type of good, right, that we consider luxury, hence the name. As was stated earlier, there are many other measures of elasticity, both demand and other types of elasticity. Here we have some examples of demand elasticity: advertising elasticity, which tells us the percentage change in demand when we increase advertising expenditures. Weather elasticity. This usually has to do with temperature, dry bulb temperature. As the temperature increases, the demand for certain goods increases or decreases. You can do it with humidity. Interest rate elasticity: as interest rates increase, the demand for certain goods increase or decrease. We can also do this for supply. Basically, we can measure elasticity for any two variables that have a relationship between each other. We have an example. Here we have a demand function, a regression type function, where x is the quantity demanded for x, p of x is the price of x, p of y is the price of a related good, y, and I is income. What we're going to do now is we're going to find the own price elasticity of demand, income elasticity, and cross price elasticity of demand. Start with our own price elasticity of demand. To do this, we simply take our formula, which we know is the partial of x with respect to px multiplied by px divided by x. I take our original formula. As you can see here, the partial of x with respect to px is negative b. Going back, I substitute in negative b for the partial of x with respect to px, and I have our own price elasticity of demand, which is negative b multiplied by px divided by x. Next is income elasticity. We know that income elasticity is simply the partial of the demand for x with respect to income, I, multiplied by income divided by the demand for X, I over X. I take the partial of X with respect to I and look at the demand formula and I get D. I multiply that by I divided by X and I get D multiplied by I divided by X. Uh, and that is our income elasticity. Now, if D is positive, then this good, X, is a normal or superior good. If it's negative, next we estimate cross price elasticity of demand. This is simply the partial of the quantity demanded with respect to the price of Y multiplied by the price of Y divided by X. Well, as we can see, the partial of X with respect to P of Y is simply C. I multiply that by P of Y over X and I get our cross price elasticity of demand. Now, if C is positive, Y is a substitute, and if C is negative, Y is a complement. I would like you now to pull out a piece of paper and something to write with and write down the Marshallian demand function that you see on the screen. I'm going to ask you to calculate the own price elasticity, the income elasticity, and cross price elasticity of this demand function. In a while, I'm going to ask you to hit pause and work on those three elasticities. After which, you can resume, and there will be a slide of 30 seconds each with the answers. If 30 seconds isn't enough, you can go ahead and hit pause on either one of the slides. This will conclude the part of the class that covers utility theory or theory of the consumer. Afterwards, we will start with theory of the firm. Please hit pause now. We are starting a new section in class called theory of the firm. Uh, this theory of the firm mechanically is very similar to utility theory. Uh, Conceptually, it's just the opposite of utility theory because these are the people that sell to consumers. As we said, we're going to deal with most problems by thinking about some decision maker who has some goals and who faces certain limitations on their ability to achieve these goals. We try to describe some optimization process by which agents decide which actions to take to achieve the goals subject to those constraints. That process tells us something about the behavior. Then we change the limitations that the agent faces and ask what will occur in behavior. We did this in utility theory, and we're going to do the same thing with theory of the firm. In the case of the consumer, they have preferences, utility functions, and they face a budget constraint. We ask what were the changes in behavior due to changes in the budget constraint. Now, this same methodology can be used to discuss the theory of the firm, although in reverse. There are different environments in which these firms operate, and we will talk about some of those different paradigms later on. Competitive firms, monopolistic firms, oligopolistic firms. Some of those environments, we will talk about how a change in the limitations could lead to changes in behavior. We can ask, for example, if a change in price the firm pays for its inputs or charges for its outputs may lead to a change in what the firm chooses to do. Constraints. Under utility theory, we have the budget constraints. For the firms, we're going to have something a little different known as an isocost, which we'll talk about later. The constraint of the firm will have something to do with the environment they're in. For example, opportunities, technologies, or reactions of other firms. Changes in technology that can change the firm's constraints. Under utility theory, the goal of the consumer was to maximize his satisfaction or utility. The firm is a little more heterogeneous in what its goals might be. Some possible examples of this might be profit maximization, cost minimization, sales maximization, revenue maximization. An example of a firm that could have a goal of cost minimization is one that's run by the government. For example, here in Puerto Rico, the Tren Urbano. Its goal is not to maximize profits, but it might be to provide a certain level of service in the least expensive way possible, or to mandate or provide a maximum level of service subject to not making a loss. We have many possible models. Each will be relevant under a particular kind of situation. Behavior. Under utility theory, the behavior of the consumer was basically what bundle of good he chose. In other words, what goods he bought. For the firm, we're going to be asking questions such as how much does the firm produce? How much does it charge? How many inputs does it buy? Etc. One of the constraints the firm faces is its technology. We're going to measure technology with a production function. A production function is a function that states the relationship between a set of inputs the firm uses and its output. We can think of the case of the consumer. The product function are similar to the utility function. Utility functions allow us to derive utility as a function of the goods consumed, while the production function allows us to derive a level of production from a given level of inputs. So output is simply a function of the inputs used. We have an example of a two-variable Cobb-Douglas production function, where Q is a function of capital and labor, where capital is raised to alpha power multiplied by labor raised to the beta power. Like in utility theory, we can learn a lot by analyzing these functions at the margin. Let me say a little about the Cobb-Douglas production function. We've actually used a Cobb-Douglas utility function because it's easy to work with. But in reality, Cobb-Douglas are two economists that studied firms and found that most firms had a production function or a split of production between capital and labor that was very similar to the function they came up with. Hence the Cobb-Douglas production function. Marginal product. Marginal product is simply the added production gain from increasing inputs by 1 unit. This concept is similar to marginal utility, where we increase a good by 1 unit and see how much utility increases by. In this case, since we have capital and labor, we're going to have a marginal product for capital, the marginal product of capital, which is simply the partial of output with respect to capital. And we have the marginal product of labor, which is the partial of output with respect to labor. Diminishing marginal product. For the most part, we'll assume diminishing marginal product in much the same way we assume diminishing marginal utility. What this means is, as we add more inputs, production may go up, but the last unit of input adds less to production than the unit before it did. What this means is that the first derivative may be positive, but the second derivative should be negative. So if I take the marginal product of capital, I want to take the partial derivative with respect to capital. That gives me the second derivative, and it should be negative. I do the same thing for the marginal product of labor. I take the partial with respect to labor, and that second derivative should be negative if we have diminishing marginal product. Marginal product is difficult to measure empirically, therefore, in the literature, sometimes you'll see average product referred to. Average product is simply the total amount produced divided by one of the factor inputs. For instance, the average product of labor is the total amount produced divided by the amount of labor used. The average product of capital is simply the total amount of production divided by the amount of capital used. Isoquants. Say we have a single output and two inputs, y1 and y2. We may want to look at combinations of the two inputs that can produce the same level of output. Say the point in figure A on the next slide, right, are 2 points which can produce the same amount of omelets. Each one uses a different proportion of eggs and labor. One uses a relatively smaller amount of eggs and more labor than the other one. Now later on we're going to see isoquants are very similar mechanically to indifference curves. For now, let's concentrate on the 2 points on the figure below, and the next slide that is. As you can see, I have 2 points here, both of which produce one omelet. The lower point, right, has more of y1 and less of y2, while the higher point has more of y2 and less of y1. These we can interchange as eggs and labor. I may want to assume constant returns to scale. This would mean that I can produce anywhere along the rays from the origin of the figure below. So far, all my technology has described is a production set that consists of these two rays. In figure B, the next slide, don't be concerned with the arrows. All they're doing is pointing to the fact that each of the points produces one omelet. The arrows aren't part of the graph. It's just like figure A above, but we're adding the rays from the origin. As I said above, I take the point from the origin and draw a ray that goes through each of the points, and anywhere along that ray I can interchange labor and eggs in the same ratio and produce somewhere along that ray where the dot would equal one omelet on each ray. Again, the arrows, don't pay attention to them. They just signify it's one omelet. I also want to assume convexity. This would mean that I can produce one omelet using a linear combination of these two techniques. For example, I could produce half an omelet using one technique and another half an omelet using another technique. If we had additivity, we can produce a whole omelet by producing half an omelet in each particular way, just like figure C below. Or I can produce a whole omelet using a convex combination of the two techniques, as we'll see in the next graph. Here in figure C, you see the two bottom dots produce half an omelet each, hence arrows pointing down to half an omelet. The other three dots up top all represent one omelet each. Now I can produce one omelet on each of the rays on those dots, or I can produce one omelet with the linear combination, in this case a convex combination, of those two dots. And that would be the middle dot. That is the middle dot in between the two dots on the rays. If I add free disposal, it means that I can also produce one omelet using arbitrarily more of factor 1 and arbitrarily more of factor 2. If I look at figure D above, I take the 2 points on the ray from the origin and draw other lines out away from the origin. I can also, anywhere on that line, get a point where I can produce at least one omelet. This is because I'm using more of both factor 1 and factor 2. Now, if I had 3 different ways of producing omelets by taking the convex combination, right, I would get figure E below. Note it's starting to look a lot like a convex set, much like our indifference curves. I'm going to produce a convex hull from all the different activities that are available to me. If I have several ways of producing that one omelet, the lower hull would be the most efficient way of producing that single omelet. See figure F on the next slide. If I have lots of different activities, ultimately I would end up with some convex surface like the one in figure F, and this is what's going to be called a unit isoquant. It's called a unit isoquant because I'm producing one unit of output. Uh, from that, we can have more isoquants that produce more units of output. Notice it looks a lot like an indifference curve. These are all the points that produce one omelet. Notice I've created that lower hull, which is convex to the origin. This, as mentioned earlier, is our isoquant. In general, an isoquant depicts a situation where the same level of production can be achieved using different combinations of inputs. Mechanically, as mentioned many times before, it looks a lot like an indifference curve. But instead of having the same amount of utility throughout the curve, we have the same amount of production. This, of course, is that now we're analyzing production, while when we use the indifference curve, we were analyzing utility. Of course, the indifference curve is derived from the utility function, while this isoquant is derived from the production function. The marginal rate of technical substitution. The marginal rate of technical substitution is simply the rate at which the firm has to substitute one input for another while keeping production constant. In other words, it's the slope of the isoquant. Again, it's very similar to the marginal rate of substitution in utility theory. So it's simply the change in capital divided by the change in labor, keeping Q fixed. To derive the marginal rate of technical substitution, all we have to do is take the total differential of the product function. Notice we end up with the marginal product of labor and capital multiplied by the change in labor and capital respectively. That is the marginal product of labor, dL, plus the marginal product of capital, dk. Since we are remaining on the same isoquant, Q is constant, therefore the change in Q is 0. So I can rewrite the equation as follows. The marginal product of labor dL equals negative the marginal product of capital dk. I can go ahead and write the slope, therefore, dk dL equal to the marginal product of labor over the marginal product of capital. That is, the slope of the isoquant, the marginal rate of technical substitution, is equal to the ratio of the marginal product of labor and the marginal product of capital. As we saw, indifference curves were convex to the origin, and therefore the marginal rate of substitution was diminishing throughout. Well, isoquants are also convex to the origin, and therefore will have diminishing marginal rates of technical substitution. To see this, all we have to do is take the derivative of the marginal rate of technical substitution with respect to labor or capital. Since labor is on the horizontal axis, we'll concentrate on labor. The marginal rate of technical substitution is simply the marginal product of labor over the marginal product of capital, so I take the partial of this with respect to labor. Because the marginal rate of technical substitution is a fraction, we're going to have to apply the quotient rule. And because f of k and f of L are both functions of k and L, we're going to have to apply the chain rule within there. So we can see below, we'll get the following. The marginal rate of technical substitution is a fraction, we have to apply the quotient rule. And since both the marginal product of labor and capital are functions of both capital and labor, we'll also have to apply the chain rule within. So, using the quotient rule in the numerator, I get f of k times the derivative of f of L with respect to L. Now, L affects f of L both directly, that's f of LL, and indirectly through k. and that's why we have the second point. I have f of lk multiplied by dk dl. Now, the second part of the numerator of the quotient rule, I have f of l times f of k with respect to l, and of course, f of k, excuse me, f of k will be affected by l both directly and indirectly. So we get f of kl plus f of kk times dk dl. Since by assumption f of ll and f of kk are 0, and by Young's theorem f of kl equals f of lk, and finally we assume that f of lk is greater than 0, and therefore the derivative of k with respect to l is going to be the ratios of the marginal product of labor over the marginal product of capital, negative of course, so we get negative f of l over f of k. Using these, I can rewrite the above, that's marginal rate of technical substitution with respect to labor, as follows in the next slide. So using these facts, I can manipulate this equation. I start in the first line here, or the first equation, simply substituting in negative f of l over f of k for dk dl. And the next line, I go ahead and I manipulate a little more, first noting that in that f of k divided by f of k is 1. So the first part of in the numerator, I get f of k, f of ll, plus f of kl times negative f of l, because the f of k's cancel. And then in the second part of the numerator, I get f of l, f of kl, plus f of kk, f of l squared, that's f of l times f of l, over f of k. And of course in the denominator, which I forgot to mention earlier, I got f of k squared. With some manipulation, I get the following. F of k over f of k times f of k times f of l. Notice I'm just multiplying by 1 now. F of k over f of k times f of kl minus f of lk. F of k over f of k, f of l, f of lk, plus f of kk, f of l squared over f of k. Again, just multiplying some of these variables in the numerator by 1. And of course in the denominator I still have f of k squared. With just a little bit more algebraic manipulation, we get the following. In the numerator, I get f of k squared times f of ll minus 2 f of k f of l times f of kl plus f of l squared times f of kk divided by f of k cubed. Now this is negative. To see this, just look at each individual element. In the numerator, the first element, I get f of k squared, which is positive, multiplied by f of ll. Now that's a second derivative, and by assumption that's negative, so the first element is negative. The second element, I have negative 2 times f of k, which is positive, f of l, which is positive, and f of kl, which is positive. Since I have the negative sign in front of it, the second element is negative, therefore. The final element in the numerator, I have f of l squared, which is positive, times f of kk, which by assumption is negative. So all the elements in the numerator are negative, and in the denominator I have f of k, which is positive. I cube it, it remains positive. So I have negative over positive, I have negative. This means my isoquant is going to be convex. Now that we've seen that the isoquant has diminishing marginal rates of technical substitution, I want to talk a little more about some of the other properties of the production function. The first one is returns to scale. This concept allows us to examine what happens to production while all inputs are increased by the same percentage. For instance, if I increase both capital and labor by 10% and output increases by 10%, we have constant returns to scale. If I increase both capital and labor by 10% and output increases by less than 10%, I have decreasing returns to scale. And finally, if I increase both capital and labor by 10% and output increases by more than 10%, I have increasing returns to scale. The next thing I want to talk about is elasticity of substitution. This is the measurement of the proportional change in the ratio of capital to labor relative to the proportional change in the marginal rate of technical substitution along the isoquant. For the production function, Q is a function of K and L, the elasticity of substitution can be represented as follows. That's sigma, the percentage change in capital over labor, divided by the percentage change in the marginal rate of technical substitution. Since it's this elasticity measure, we can use the elasticity formula that we've used before. That is, take the derivative of capital divided by labor with respect to the marginal rate of technical substitution and multiply that by the marginal rate of technical substitution divided by the ratio of capital over labor. Now, the percentage changes can be approximated using the natural log function. In this case, we can rewrite that as the partial of the log of the ratios of capital over labor with respect to the ratio of the marginal product of capital over the marginal product of labor, which, as we know, is the marginal rate of technical substitution. Go ahead and see the text for examples of production functions with different elasticities of substitution. What I'll talk about is technical progress. With improvements in the production process, more output can be obtained with the same combination of inputs. We can represent this with a parallel shift in the isoquant. We can denote this mathematically by putting a shift parameter, A of t. Since we assume technology will improve with time, we can write this and all other variables as a function of t, time. Notice here, t denotes time, unlike before where it was simply a random parameter. So I can write q, a of t, f of k, and l. Now, pay attention to what we're going to talk about here, because in all likelihood you're going to see this again in macroeconomics. Okay, let's do a little bit of algebraic manipulation before we continue. Q is equal to A times our production function. So therefore I can write our production function as Q over A, or I can write A as Q over our production function. Now, as mentioned earlier, every variable in our production function, A and K and L, are functions of t. Therefore, our production function, right, is a function of t. So when I take the derivative of output with respect to t, I can use the product rule, and I'll get the derivative of A with respect to t times our production function, plus A times the derivative of our production function with respect to t. Now, manipulating this a little, using the fact that our production function equals Q over A, and A equals Q over our production function, I can rewrite this as dA dt over Q over A, just replace our production function there for Q of A, plus Q over F of L, which used to be A, times the partial of F with respect to K times dk dt. Now we're just using the chain rule. T affects capital, and capital affects our production function. And the second part of this is the partial of F with respect to L times dL dt. Again, time affects labor, and labor affects our production function. Now, with some algebraic manipulation, and noting that Q equals A times F, I can divide the equation by Q, and I get the following. dQ over dt divided by Q is going to equal dA dt over A. Now, I'm left with A because F, the F's cancel. Then I get the partial of F with respect to K, F of KL, dk dt. Notice in this case, the A's will cancel, plus the partial of F with respect to L divided by F dL dt. Now, with a little bit more manipulation, I can get the following. I multiply the second element by 1, k over k, and the third element by 1, L over L, and I get the following. Right? The first element remains the same, dA over dt over A. The second element I could write now is a partial of f with respect to k over f, dk over dt over k. And now the third element is very similar, f of the partial of f with respect to L over f, dl dt over L. If you pay close attention, you'll notice that most of the elements in this equation are growth rates. Rather, each element has a growth rate in it. The first element is a growth rate of nothing more. It's the change in A divided by A. The other two elements, right, have a growth rate. The second. Now we can examine growth accounting. As I said, you'll probably see this again in macroeconomics next semester. We can rewrite the equations that we had above to denote how production changes relative to growth in technology and inputs, as well as elasticity of output with respect to its inputs. So our growth in production is going to equal the growth in A, that's technological change, the elasticity of production with respect to capital, multiplied by the growth rate in capital. So capital will affect the growth rate of production two ways. One, it'll be by how much capital grows, in other words, how much we put into capital, and the elasticity of capital. And finally, the same thing for labor, the elasticity of labor times labor. So you see here, we just rewrite the equation here. The partial of f with respect to k multiplied by k times f, right? And that gives us the elasticity of output with respect to capital, GK, the growth rate in capital, times the elasticity of output with respect to labor, times the growth rate in labor. And that concludes this lecture. As I said, that concludes the lecture. If you have any questions, you can email them to me or wait till I get back in town. If you have any feedback onto how I might be able to make this video presentation better, it's very much appreciated. Thank you very much and have a great week.